Hi, this is the sixth lesson in waves. See the description of this video. All the useful links related to my other videos are given there. Also, by using the playlist of this channel, you can navigate to any video that you want to watch. Something like if you want to see a video related to past paper discussions, all my videos are grouped into different category like Unit 1 lessons, Unit 1 past paper discussions, Unit 2 lessons, Unit 2 past paper discussions, like Unit 4 lessons, Unit 4 past paper discussions, and so on. So by using the playlist of this channel, you can navigate to any videos you required. Okay, so in this channel, I'm going to discuss, this is the sixth channel. In this lesson, I'm going to discuss about diffraction grating. Okay, what is diffraction grating? It's a component that is used in experiments related to waves. We learned already in my previous lesson, in fifth lesson, about young slit or double slit. So double slit means they are on a non-transparent sheet. There will be just two slits and light can pass through those double slit, and they will diffract, and diffracted waves will superpose. And if you keep like something like this, we learned that in the previous lesson, unit 5, in my fifth lesson. When you have double slit, something like this, and if you keep a screen here, when light passes through the double slit, the light will diffract through the two slits, and these diffracted lights will overlap on the screen, and that will create alternatively bright and dark fringes. And by using this double slit, we can measure the wavelength of the unknown wave. There's an equation, but not in your syllabus. That equation says lambda equal to x s over d, not in your syllabus, where x is the fringe separation. This is the bright fringe, then you will get dark fringe, then either side there will be dark fringe, then bright fringe, dark fringe, like that. You will get alternatively bright and dark fringes, central maximum, first minimum, first maximum. I already explained that in my lesson 5, waves, fifth lesson. And where lambda is the wavelength, x is the fringe separation, distance between the two adjacent bright fringes, this is x, and s is the distance between the two adjacent slits, s, and d is the distance between the screen and the double slit. These are related by this equation, but we don't use this in your syllabus, so I don't want to go in detail about that. Okay, so this is double slit, we call it young slit or double slit. So what is diffraction grating means? Diffraction grating also something like this, but it gives very clear, well separated bright fringes. There we don't consider the dark fringes, or we call in diffraction grating, the bright fringes are called bright bands, or we can call bright bands also, or bright fringes. It consists of diffraction grating consists of several hundreds of slits. It could be 300 or 400 or 500 slits in 1 millimeter width. In 1 millimeter width, there could be 300 slits or 500 slits or 400 slits. So because of many slits in small region, what happens? Through each slit, when light passes, there will be diffraction, and these diffraction waves will overlap, and finally they'll have constructed superposition, and they'll form bright fringes or bright bands on the screen. The advantage of diffraction grating compared to double slit, when we use diffraction grating, the bright bands will be well separated on the screen. So easily we can measure the distance between the adjacent bright bands or bright fringes. By using even meter rule, we can easily measure. But in double slit experiments, it's difficult to measure the distance between adjacent bright fringes because they are very close to each other. We need to use a traveling microscope. Normally, we use traveling microscope to measure the distance between adjacent bright fringes when we use young slit or double slit. But when we use diffraction grating, the advantage, the distance between the adjacent or the next to next bright fringe or bright band, either word we can use, distance between adjacent bright fringes could be measured by using just meter rule or ruler. So that's the advantage of diffraction grating. It creates well separated, clear, bright fringes. We don't use any dark fringes here. We don't need any dark fringes. We don't use the dark fringes in diffraction grating. Okay, so this is the enlarged diagram of a diffraction grating. In 1 millimeter, there could be around 500 slits or 600 slits. So it's an enlarged diagram. So when light passes through all the slits, what happens? The light will diffract through all the slits. Difficult to draw. Light will diffract through all the slits, and these diffracted waves will superpose. So normally when we draw, we don't draw like this. We don't, actually the light will pass through all the slits. That's very important, because the thickness of the light, the width of the light ray we are using should cover the whole slit. So if it is 500 slits per millimeter, means the light which is coming out of the laser torch should pass through all the slits. Otherwise, the other slits won't be used in the experiment, right? So, but here it looks like several centimeter width. I drew it because otherwise difficult to explain by using a board. So here the light will pass through all the slit, and the light will diffract through all the slits, and diffracted lights will superpose. So we don't draw the diffraction of light waves when we teach, and most of the books, they don't show the diffraction pattern of the lights passing through each and every slit. We normally draw the final outcome like this. I'm going to draw that one now. Okay, so this is the enlarged diagram of diffraction grating and the pattern, the diffraction fringes formed due to diffraction grating. So the diffraction grating, remember, the whole light will pass through all the slits on the diffraction grating, not through one or two. Otherwise, you won't get use of the complete outcome won't be there. So the light, the width of the light or the thickness of the light ray must cover all the slits in the diffraction grating. Okay, so when the light passes through diffraction grating, so we don't show the diffracted waves or anything. We normally show by using these rays. Okay, the light which exactly pass straight. Okay, so there will be a bright band or bright fringe where the light it's like it's along the same line of the initial direction of the light ray. So this light ray, it looks like this this bright fringe is formed something like along the same line of the initial ray. So this is called 0th order. We don't call central maximum. This is called 0th order bright fringe or bright band. On either side, the next bright bands are called first order. First order. This is also called first order. In double slit, we call central maximum first maximum. Here we call first order bright band or bright fringe. This is called 0th order. I can write in word 0th. Same way, this is called second order. This is also second order. So the bands, those are formed on the screen, are symmetrical about the 0th order on the either side. Okay, so the notation we use for order is n. So we use this is n equals 0, n equal 1, this also n equal 1. N is used to denote the order, n equal 2, n equal 2, and so on. There can be more order of bright bands, n equal 3, n equal 4 also can come, can be produced, but we can calculate later. We are going to do questions. How many orders of bright bands could be seen? There's a limitation. It can't be infinite number of orders. There will be limit. So we are going to calculate that by using the equation. But anyway, you should know the bright bands are well separated like this. So in this region, we can call dark band, but we don't use anything about the dark region, or if where there is no bands formed, those regions we don't consider in this experiment. So the bright bands or the bright fringes are well separated like this. So the light ray along the initial direction is called 0th order. So here we consider angle of diffraction or the angle from the deviation from the initial direction. This is we can call theta 1. This angle we can call theta 1. This also theta 1. This is theta 2, the amount of diffraction of the angle. This is theta 2. So theta 1 is the angle of diffraction compared to the initial direction of light ray, the angle of diffraction for the first order. Theta 1 on the other side also, on either side this identical or the similar patterns will be formed. So in this direction upwards, the angle of diffraction for the first order is theta 1. On the other side also, the angle of diffraction for the first order, theta 1. Same way, the angle of diffraction for the second order, theta 2 on this direction. In this direction also, the angle of diffraction is theta 2. So the angle of diffraction, how do we measure? The angle of diffraction is measured relative to the initial direction of the light ray. So the angle of diffractions are always measured relative to initial direction of the light ray. Again, I am telling the bright band or the fringe formed along the initial direction of the light ray is called 0th order. Either side, first order, second order, and so on. Okay, so the angle of diffraction or angle of deviation of the light ray for the first order, theta 1, for the second order, theta 2. Remember these things. Okay, so experimentally, how do we measure the angle theta 1 or theta 2? We don't use any protractor, just by using trigonometry and the measurements on the screen and the distance of the diffraction grating from the screen, we can calculate by using tan theta. If I know the distance of the screen from the diffraction grating, that could be measured by using meter rule, not a big thing. We normally keep it at a distance of 1 meter or 1.2 meter, 2 meters, no problem. You can keep such larger distance like that. So if I know that distance of the screen from the diffraction rate, if I call that distance D, capital D, if I call that this as capital D, and I can measure the distance of the first order from the 0th order on the screen. If I am focusing the diffraction, if I keep a diffraction grating in front of clear white wall, and if I keep a laser torch behind it, I can see the dots or the bright dots on the wall. Wall could be used as a screen. There I can measure the distance of first order from the 0th order, second order from the 0th order. Like that I can measure the distance. It's not a problem. Very simply you can measure by using meter rule. So if I know this distance, if I name the distance of the first order from the 0th order, if I call this x1, here also x1, both will be same, either side same, but my diagram is not clear. But this x1 and this x1 are the same. I couldn't draw exactly the same way. I can simply use the trigonometry tan theta. I can find the angle theta 1 by using tan theta 1 equal x1 over d. I know x1, I measured it on the screen by using meter rule. I know the d, distance of the screen from the diffraction grating. So I can calculate the theta 1 by using tan theta 1 equal x1 over d. Same way, the angle theta 2, how can I measure? If I know the distance of this one, distance of second order bright band from the 0th order, if I know that distance as x2, this one, this as x2, here also it will be x2 on up this direction. They are same, both x2 must be same. If I say this is x2, then I can find the angle theta 2 by using tan theta 2 equal x2 opposite over adjacent d in this right angle triangle. In this right angle triangle, I can use tan theta 2 equal opposite, which is x2 over d. This is the way we measure the angle of diffraction, not by using protractor. This is the way we calculate the angle of diffractions. Okay, so there's an equation that relates the wavelength, the distance between the next to next slits or adjacent slits on the diffraction grating, the angle of diffraction for a particular order n. Okay, so that derivation is not in your syllabus, but that equation is given in the data sheet. So just your questions are based on calculation based on these equation. This equation. Only one equation you have related to diffraction grating. One equation is that one. I'm going to write it now. The next one is you might need to find the angle theta 1 by using tan theta as I shown now. Okay, so the equation that we use for diffraction grating, which is given in the data sheet, is given by d sine theta equal n lambda. Derivation you don't need, so I'm not going to derive it. Okay, so each and every quantity you must know what do they mean. So here d means the distance between the next to next slits, or distance between the adjacent slits. So if I draw the slits like this, on a diffraction grating, so there are several slits in 1 millimeter. So what is d means? D is the distance between the next to next slit. This is d. Same way, this is d. This is d. So that is d. Okay. How to calculate d by using diffraction grating? I'll tell you. So that is d. D is the distance between the nearest slits or distance between the adjacent slits. Okay, sine theta, where theta and n are related to each other. What is theta? Here theta is the angle of diffraction for the order n. Say for example, for first order, and you can say n equal 1, if you substitute n equal 1, then theta should be theta 1. N equal 2, theta must be theta 2. So what is theta means? Theta is the angle of diffraction. Or some books they say, they don't use the word angle of diffraction, they say angle of deviation from the initial direction of light ray, both say. So that theta, so the theta is the angle of diffraction or the angle of deviation from the initial direction of light ray for the nth order, first order theta 1, second order theta 2, and so on. Lambda is the wavelength of the wave we are using. So if you are using a monochromatic light ray, that wavelength we should consider. If you are using white light, it consists of 7 colors, 7 different wavelengths. So each and every wavelength will follow their own diffraction and they will create their own fringes on the screen. So they'll create, I'll tell about that later. So when white light is used, each and every wavelength will form its own bright fringes on the screen, right? And different wavelengths will have different amount of diffraction, so they'll create different bright bands on the screen. Okay, so the equation related to diffraction grating is d sine theta equal n lambda. You should know certain things related to diffraction grating. You must know, because the calculations you can do, but sometimes there could be statements in the MCQ question. So the first thing you must know how to calculate the D when they give number of slits per millimeter. For example, if the question says a slit consists of a diffraction grating consists of 500 slits per millimeter. A diffraction grating consists of 500 slits per millimeter. Then how to calculate the D? What do you mean by 500 slits per millimeter? Means in 1 millimeter width there are 500 slits. I can say there are 500 slits in a length of 1 millimeter. Okay, so what's the distance between the adjacent slits? We can say that is D is equal to 1 over 500 millimeter. we can give the d in terms of millimeter, 1 over 500 millimeter. If you solve it, you will get 1 over 500 will be equal to 2 into 10 to the power minus 3 millimeter. So the distance between the next to next slits or the adjacent slits, we can calculate by using, remember the method, 500 slits are arranged in 1 millimeter width. So the distance between the adjacent slit is given by d. That's a notation we use. D is equal to 1 millimeter divided by 500 in millimeters. Or you can find in meters. Normally the question is based on meters because normally the wavelength is given in meter in this equation. So if the lambda is given in meter, d should be meter. The equation should be symmetrical or homogeneous. Okay, so if I want to find the d in meters, I can say 500 slits are in 1 millimeter means 1 into 10 to the power minus 3 meter. 1 millimeter means 1 over 1000 meter. Now just find the d. So d will be equal to 1 into 10 to the power minus 3 over 500 meter. That will be equal to 2 into 10 to the power minus 6. That's the way we find the d. You must know the first point. I'll tell point wise what things you should know related to diffraction grating. The first point, you must be able to find the d if when they give number of slits per millimeter. Okay, so the second point you should know that is on the screen, this is the 0th order, this is the first order, second order bright bands or bright fringes. The distance of the first order from the 0th order is x1. Distance of the second order from the 0th order is x2. Normally students, they ask the gap or the distance between 0th order and first order, will it be same as from first order to second order? No, it won't be the same. Same way, the distance from second order to third order, I didn't draw the third order, right fringe, but the distance between the second order and the third order, will it be the same? No. What happens actually, that better to know that because it could be a statement in the MCQ. The distance of the 0th order to second order, 0th order to first order to second order, when we consider, the distance increases. From 0th order to first order, when we compare, if I say that distance is x1 and the distance of first order to second order, that will be x2 minus x1, or I can call that as I put that from the 0th order to second order, I put it as x2. So that will be x2 minus x1. So that gap will be more than x1. So the distance increases from the 0th order. When you consider other orders, the distance between the adjacent bright bands will increase. The reason, if you ask, is actually due to the trigonometric relationship. You know, d sine theta equal to n lambda. For imagine it's a monochromatic light, one wavelength. So d sine theta equal to n lambda. Okay, if you want to find the theta 1, so sine theta 1 equal to n, we'll put 1 because it's the first order. So 1 into lambda, so it will be lambda over d when n equal 1. Same way, sine theta 2 is equal to, I should put n2 because I am finding the angle of diffraction for the second order bright band or bright fringe. So that should be 2 lambda over d. So sine theta 2 becomes 2 times of the sine theta 1. So that is the value of sine theta 2, which is 2 lambda over d, is twice the value of lambda over d. Now think about the sine graph. Little bit unwanted thing, but anyway, sometimes students might be interested. That's what I'm doing. If you think about the sine graph, this is sine theta against theta graph when you consider. So you know the maximum angle of diffraction when a fringe is formed is 90 degree. Theoretically, it should be 89.999. We can say almost 90. So when I consider the graph for sine theta against theta graph for the first order within 90 degree, the graph will be something like this. You know the shape of the graph is like this. Sine graph is something like this, is it? This is the shape, but when I consider up to 90 degree, I don't need to consider the other parts. Okay, so here what happens? Think little bit. So the sine theta, for this sine theta 1, if I say lambda over d, this is twice. So this sine theta 1, if I find theta 1, for theta 1 is here, the value of that is this one. The other one is double of it. So compared to this side, 2 times. When you consider twice the value, this will be more than the gap. You can see this angle from 0 to this angle, theta 2, this angle or the gap between theta 2 minus theta 1 is more than theta 1 because the graph is bending this direction. That's the reason, the sine shape of the graph. So the angle theta 2 will be not double of theta 1, it will be more than the double of theta 1. I can take an example. For example, if you think like this, sine theta, just I am doing it not exam view, just for the understanding. So if I say sine theta 1, just example 0.2, sine theta 2, then it should be double of it. Is it double value? That will be 0.4. Sine theta 3, it will be triple because when you put 3 for that. Triple. So that will be 3 times of this one, means 0.6. Okay. For this, if you find theta 1, use the calculator and find theta 1, you will get theta 1 is equal to 11.54 degree. Here if you find theta 2, you will get 23.58. See, not double, more than double. Here if you get theta 3, that will be 36.87 degree, not 3 times of this one, more than 3 times. So remember the interval between the adjacent angles will increase when the order increases. So what will happen? Now think about tan theta. When you use tan theta is equal to x over d, from x over d. So theta is increasing. So the theta increases, tan value also increases the same way. For a given d, the x will be not evenly, it won't be even gap, the values won't be even, that also will increase. That's the reason x1 and the x2 minus x1 won't be same. X2 minus x1 will be larger than x1. Anyway, you don't need this mathematical explanations a little much, too much, but anyway, I just did it. So, but you must know the gap between the adjacent bright bands formed on the screen won't be the same, it will increase. When we move from 0th order to higher order, the distance between the adjacent bands will increase. Better remember that. Okay, so the third point that you must know, when the wavelength increases, for the same order, the angle of diffraction theta will increase. For example, think like this, both blue color light and red color light, both are passing through the diffraction grating at the same time. So blue color light will form its own diffraction pattern, own bright fringes pattern on the screen. Same way, red color light also will form its own bright bands on the screen, but they might overlap in a different way. We are going to do a calculation later, but red color light will form its own bright bands on the screen. Blue color light will form its own bright bands separately on the same screen. So how the first order of the blue color light and the first order of the red color light appear, we can analyze like this. D sine theta is equal to n lambda. So sine theta equal n lambda over d. Right. So when I consider blue color, sine theta 1, the first order of the blue color light, sine theta 1 equal n equal 1 times lambda blue over d. That is lambda blue over d. For red color, if I consider, sine theta 1 equal, for red color also n equal 1, I am considering the first order, 1 into lambda r over d. that is lambda r over d. Right, we know that the wavelength of red color is greater than wavelength of blue color, but both have the same d. So sine theta 1 will be larger than sine theta 1 for the red color will be larger than sine theta 1 for the blue color. So since the sine theta 1 for the red color is larger than sine theta 1 for the blue color, first order of the blue color angle is smaller than the first angle of diffraction for the red color angle. So what will happen? The theta 1 for the red color will be greater than theta 1 for the blue color. So if I can call this theta 1 r, theta 1 b. Okay, so I can say theta 1 r, the theta 1 r, that means the first order diffraction angle for the red color is going to be greater than theta 1 blue. Now we think about tan theta. Tan theta equal to, general equation we know that tan theta is equal to opposite over adjacent. So when we consider tan theta, now think about that way. So now this you understood, I think. The angle of blue color for the first order will be smaller than angle of diffraction for the first order red color. Right, now we'll think about tan theta, because we use tan theta to find the distance of the first order fringe on the screen from the zeroth order, like that. So if I consider tan theta equal x over d, d is the distance between the screen and the diffraction grating. So what happens now, for red color light, theta is larger for the first order. So tan theta 1 r will be larger. When theta increases, tan value also will increase. We know that when theta increases, tan value also will increase. So when tan theta 1 r is greater than tan theta 1 b compared to blue color, red color has large angle. So tan value of that angle is greater than tan value of blue color angle. So that increases, mean when you cross multiply the distance of the first order for the red color, distance of the first order or first bright band of the red color will be greater than distance of the first color for the blue color. So that's the reason you will see the blue color first order bright band will be closer to the zeroth order. For the red color, it will be further away. But zeroth order will form at the same position, because when n equals 0, theta is 0 for whatever the color. So zeroth order will be the same position for whether blue or red or even whatever the color you use. The zeroth order will be the same position, but smaller the wavelength, the distance of the first order from the zeroth order will be closer to the zeroth order. Smaller the wavelength, it will be closer to the zeroth order. So red color, first order will be here. First order blue color will be here. The same way, second order red color will be further away compared to the second order blue color light. Okay, and so on. So remember that this also, the first order of the blue color, if blue and red light both at the same time pass through the diffraction grating, first order blue color light will be closer to the zeroth order. First order red color bright band will be little further away from the first order blue color light. Okay, the fourth point you must know, what will happen to the bright bands formed on the screen when the distance of the screen from the diffraction grating is increased. Okay, we'll analyze it. Now we know the equation d sine theta equal n lambda. So for a given wavelength, imagine you are using a monochromatic light, one particular wavelength. So lambda is constant. For a given diffraction grating, d is constant. For a given order of the band, say for example first order n equal 1, the theta is fixed. We know that sine theta equal to n lambda over d. So the sine theta is constant when lambda d are constant. So first order angle theta is fixed whether you are changing the distance between the diffraction grating and the screen. Even if you change the distance, whether you bring the screen closer to the diffraction grating or when you move the screen away from the diffraction grating, there is no change in theta because d is constant for a given diffraction grating. Lambda is constant. You are imagine you are using a monochromatic light, and for a particular order, n and theta are related to each other. So for a particular order, the theta remains unchanged when the screen is moved closer to the diffraction grating or whether it's moved away from the diffraction grating. So theta is fixed for a particular order. It's fixed. Right. Now what will happen? But we know that tan theta is equal to x, the distance of the particular bright band, x, that means from the 0th order, its distance x over d. So we will consider tan theta 1. So when any theta equal, when we consider first order, sin theta 1 will be equal to, n has become 1, so I can remove it, n equal 1 into lambda over d. So sin theta, I am thinking about what will happen to the first order bright band when I increase the distance of the screen from the diffraction grating. What's going to happen? So n equal 1, so I can say this is when n equal 1. So n equal 1, sin theta 1 equal lambda over d. At the same time, tan theta 1 equal x1 over d. x1 is the distance of the first order from the 0th order. So d is going to be increased. Now I am going to increase the d. So cross multiply, x1 is equal to d times tan theta 1. So theta 1 has no change. I told lambda fixed, d fixed. So tan theta 1 has no change. If I increase the d, so when d increases, d is the distance between the screen and the diffraction grating. When d increases, x or x1, the distance of the first bright band or first order band from the 0th order, x1 will increase. Same way when d decreases, x1 will decrease. So when you increase the distance of the screen from the diffraction grating, the distance of the first order bright band from the 0th order will increase. The same way, the distance of the second order bright band from the 0th order also will increase. Okay, so when you are doing practical, normally we keep the a distance like 1.2 meter, 1.5 meter like that, because we should not keep the d very close, because when you are increasing the d, you know the measurement will become larger. The advantage, when the measurement become larger, percentage uncertainty, you learned that in unit 3, percentage uncertainty will become smaller. Okay, we are using meter rule normally to measure the distance. So when the d becomes larger, percentage uncertainty in that measurement will become smaller. That's the advantage when we are increasing the d, but we can't increase the d much bigger depending on the facility or the lab or the distance of the screen. We should try to keep the distance possibly maximum, because the distance of x1 also will increase. That also easy, or that will also give a smaller percentage uncertainty in the measurement of theta 1. Okay, so the fifth point you should know, what could be the outcome or what will happen to the bright bands formed on the screen when we use a diffraction grating with more number of slits per millimeter. Say for example, you are using the same laser torch, monochromatic light, same wavelength, but first practical you are doing with a diffraction grating that has 300 lines per millimeter. Then you are doing the same experiment with the same light source, same wavelength. There you are using a diffraction grating that has 600 lines per millimeter. What changes could occur on the diffraction pattern or the bright bands formed on the screen? Okay, we'll analyze it now. When the number of slits per millimeter of the diffraction grating increases for the same wavelength, what will be the change on the position, or will there be any change on the diffraction pattern formed on the screen? Okay, use the same equation, d sin theta equal to n lambda. Okay, so we find D. How do we find D? 1 into 10 to the power minus 3 if you are using the D in meter, because this is given in per millimeter. So we have to convert to meter, so 10 to the power minus 3 divided by number of lines per millimeter. Number of lines per millimeter is it? That's the way I explained when I start this lesson. 1 into 10 to the power minus 3 meter divided by number of lines per millimeter. So when the number of lines per millimeter increases, 300, 600, for just example I took it. When the number of lines per millimeter increases, the denominator is increasing, so the value of D will decrease. The value of D, the distance between the adjacent slits or nearer slits distance, will decrease. Now what will happen? D sine theta equal n lambda. So when I use a diffraction grating with larger number of slits per millimeter, D will decrease. When D decreases, what will happen? Sine theta equal n lambda over D for a particular order. Say example, we'll take first order. Easy, first order. When I take n equal 1, it will become lambda over D when n equal 1. So when the D decreases, I told the D will decrease when number of lines per millimeter increases. D decreases, sine theta will increase. So when D decreases, sine theta will increase. So I can call, because n equal 1, I can name this sine theta 1. No problem, sine theta 1. So sine theta 1 will increase. So sine theta 1 increases means theta 1 will increase. Okay, so when theta 1 increases, what will happen to the x1? We use the equation tan theta now. Tan theta is equal to, I'll write it here. So tan theta is equal to tan theta 1 is equal to x1 over d. So x1 is equal to d times tan theta 1. So theta 1 will increase. When the theta 1 increases, tan value also will increase. D has no change. We are not changing the distance of the screen from the diffraction grating. So when tan theta 1 increases, x1 will increase. So when tan theta 1 increases, x1 will increase. So I can give the final conclusion. When we use a diffraction grating with more number of slits per millimeter, what will happen? Distance of the bright bands from the 0th order will increase. First order I just took it. Same way, the distance of the second order also will increase when I use diffraction grating with more number of slits per millimeter. So all the distances all the distance of the bright bands from the 0th order will increase when we use more number of lines per millimeter. You must know this. Okay, so the sixth point, the last point related to diffraction grating, you must know. When there is something related to trigonometry, nothing related to physics, when the angle becomes smaller, that is, when the angle becomes less than 10 degree, sine theta will be equal to theta in radians. You understand what I'm saying? When the angle becomes less than 10 degree, equal to 10 degree also somewhat we can accept. When the angle becomes less than or equal to 10 degree, the sine theta will be equal to theta in radians. You know how to convert degree into radians. You know that 180 degree related is equal to pi radians. So theta degree, how much of radians? Pi divided by 180 into theta. Okay, we'll see. For example, when we consider sine 5 degree, how much? Check it from the calculator in degree mode. Sine 5 degree in degree mode, you will get 0.087. Now find how much is 5 degree in radians. 5 degree in radians, how much? Find it. Pi divided by 180 into 5 radians. So solve it, you will get exactly the same answer, 0.087 radians. So that means sine 5 degree equal to 0.087. The 5 degree in radians also the same value. So when the angle becomes smaller, something like less than 10 degrees, sine 5 degree is equal to the same 5 degree in radians. So I can say sine theta, when the angle is smaller, less than 10 degrees, sine theta is equal to theta in radians. We might use these things in diffraction grating. Sometimes if the angle of diffraction is smaller, we don't need to use sine theta. Say we know that d sine theta equal n lambda. So sine theta equal n lambda over d. So normally, how do we find theta? We use theta equals sine inverse. Sine inverse, you know, shift sign used in the calculator. Sine inverse n lambda over d. But if theta is less than 10 degree, I can say sine theta equal to theta in radians. Therefore, theta equal, I don't need to use sine inverse, theta equal n lambda over d. If the angle is smaller than 10 degrees, I can say theta equals sine inverse, I don't need to write. I can say sine theta equal to theta in radians. So theta equal to n lambda over d in radians. Okay, so now we'll discuss exam style questions. This question appeared during January 2023. Question number 8, WPH 02. Right. So here this IAL paper. So this question tells that there's a laser torch, there's a screen, this is the position of the central maximum, this is the first order maximum. The question is, which of the following changes would decrease the distance between the central maximum and the first order maximum? That means they want to reduce this length, this distance x. We know this is d. This is the angle theta, angle of diffraction is theta. So they want to reduce x, okay, which will cause that decrease in x, decreasing the distance from the laser to the grating, laser torch to the grating. This is the grating. I wrote a short sentences, right? Anyway, so this is the diffraction grating, this is the laser torch. Decreasing the distance from the laser torch to the grating, that has no effect. We know the equation d sine theta. The only two equations we consider, d sine theta equal n lambda, then tan theta equal to x over d. These are the only two equations we are going to use in diffraction grating calculations or any explanation. So these two equations are not depending on the distance of the laser torch from the diffraction grating. There is no effect, so not the answer A. Answer B, increasing the distance from the grating to the screen. If they are increasing the D, what will happen? When you increase the D, before that we should know that d sine theta equal n lambda. For a first order n equal 1, lambda is constant. For a diffraction grating, d is constant. So I already told that sine theta is constant for a given wavelength and the given diffraction grating. For a particular order, theta is constant. We are considering the first order, n equal 1, lambda is constant, not changing, d is not changing, theta is constant. So theta constant means tan theta remains unchanged. So when you increase the d, second answer, increasing the d, when you increase the d by keeping the, increase the d, tan theta remains constant. When you increase the d, when you bring cross multiply, x will increase. The question is, what will happen when they want to reduce the x and the distance decrease? If your distance decrease, if you reduce the d, x will decrease. But They are saying the D is increasing the distance from the grating to the screen, so it can't be the answer. Okay, so when you theta constant for a given angle of diffraction, theta constant for a given order, so theta constant in tan theta constant, if you increase the D, x will increase, cross multiply and see x will increase, but they want to reduce the x, so that's not the answer. B. Answer C, using a grating with more lines per millimeter. I just now explained, if number of lines per millimeter increases, we calculate D by 1 over number of lines per millimeter, in stands for number of lines per millimeter. So that is D. So when n increases, D will decrease. When D decreases for a given order of diffraction or given order of bright band, when D decreases, what will happen? Sin theta will increase, so theta will increase. When sin theta increases means theta will increase. When theta increases, tan theta will increase, so x will increase. So that also not the answer. D, using a light with smaller wavelength. Yes, when you use a wavelength smaller, lambda decreases, n remains the same first order. So lambda decreases, D no change, sin theta will decrease. Sin theta decreases means theta will decrease. So tan theta will decrease. D remains unchanged. So tan theta decreases, x will decrease. So the correct answer, D. WPH 1 2, not 0 2, I think WPH 1 2. This is January 2023, question number 8 MCQ. Okay, so this is the second question. It's a past paper question, Edexcel IAL past paper, but I can't remember which year. Okay, laser light of wavelength 650 × 10 to the power minus 9 meters directed at a diffraction grating. The grating has 50 lines per millimeter. Distance of the screen from the grating is 4 meters. Which expression gives the angle in radians between the zero order and the first order fringes? Okay, so it's not a big thing. We know that equation d sin theta equal n lambda. So we know the wavelength that is given 650 × 10 to the power minus 9, n equal 1 first order. I need to find the relevant theta. I need to find the D also. So we know 50 lines per millimeter. So D is equal to 1 × 10 to the power minus 3, because lambda is given in meter. So I should find the D in meter. Okay, homogeneous equation. So same units. 1 × 10 to the minus 3 over 50 meters. Okay, so sin theta I need to find. So sin theta equal n lambda over D. So n equal 1. So that's going to be n equal 1 means 1 into lambda. We know that 650 10 to the power minus 9. 650 10 to the power minus 9, that is lambda, over D, that is D equal 1 × 10 to the minus 3 over 50. So 1 × 10 to the power minus 3 over 50. MCQ, you don't need to do all these things, but just for your understanding, I am writing step by step. So 50 will go up, and 10 to the power minus 3, when it cancels with 10 to the minus 9, it will become 10 to the power minus 6. So sin theta is going to be 650 into 50 into, the 50 will go up, you see, 650 into 50 into 10 to the minus 9 divided by 10 to the minus 3 means 10 to the power minus 6. Okay, so that is the sin theta value. So if you want to find the theta, you should take sine inverse. So the theta should be here. The answers are not given. It's like an expression format they give. So there should be an answer like theta equals sine inverse. Theta equals sine inverse 650 into 10 to the power minus 6 into 50. Same, no? 650 into 10 minus 6 50. If they give an answer like this, okay, we can say that's the answer. So the answer should be in this format, sine inverse this much. But there's no such answer. Sine inverse is not there, but you can see the same number which is given inside the sine inverse is there. The reason, solve it and see. When you solve it, you will get 1.86 degree. 1.86 degree is the final answer. right? Theta is 1.86, less than 10 degrees. So I told them, if it is less than 10 degrees, sine theta equal to theta in radians. So they are saying in radians, not degree. In radians, the question says clearly. So we know that if I find it in degree, it's going to be 1.86 degree, which is less than 10. So if it is less than 10, I can say sine theta equal to theta in radians. So I don't need to find this way because I'll get answer in degree. But I know in radians, sine theta equal to theta in radians. So therefore, sine theta equal to theta means I should write this way. Theta is equal to 650 into, I'll put the 10 minus 6 first, then 50 in radians. So the correct answer B, because it's less than 10 degrees. That's the reason. Okay, question number 3. So, in an experiment, blue light of wavelength 450 nanometers is directed towards a diffraction grating and the bright fringes will appear on the screen. Grating has 600 lines per millimeter. Find the angle between the first bright fringe and the second bright fringe. Angle means angle of diffraction. So, we know this is the diffraction grating. This is the screen. So, blue light is creating bright fringes or bright bands. So, this is the straight line. So this is the 0th order, this is the first order n equal 1, this is the second order n equal 2. This is n equal 2. So the angle for the first order theta 1, angle second order theta 2, we need to find theta 2 minus theta 1, that's the first part question. So it's not a big thing. We have to find the theta 1, theta 2 separately by using the equation d sine theta equal n lambda. So the first part, we need to find the d first. D is equal to 1 over number of lines per millimeter. We need to find it in meter. So 1 into 10 to the power minus 3 meter divided by 600. So there you will get 1.667 into 10 to the power minus 6 meter. Okay, d sine theta equal n lambda. So for the first order theta 1, so d we know 1.667 into 10 to the power minus 6 sine theta 1 equal 1 into lambda given wavelength 450 nanometer. Find the sine theta 1 and theta 1. You know how to solve it. Use calculator. Divide this by this. Sine inverse will give it in angle. So theta 1 you will get 15.7 degree. Same way we can find the theta 2, that is 1.667 into 10 to the power minus 6 sine theta 2 equal to 2 into n equal 2 into second order 450 into 10 to the power minus 9. So find the theta 2, so that you will get 32.7. So the question is find the angle between the first bright band and the second bright band. So theta 2 minus theta 1, that's the first part. 32.7 minus 15.7, so it will be 17 degree. Okay, second part, find the total number of fringes or bright fringes seen on the screen. So I just drew 2. So same way we can have on either side of the 0th order. So there will be first order here, then second order here also, n equal 1 here, n equal 2. But we don't know how many orders could be formed, how many order of bright fringes or bright bands could be created. So for that we can calculate by using the equations. We can use the equations d sine theta, second part, d sine theta equal n lambda. The maximum value of angle of diffraction, theoretically the maximum value of angle of diffraction theta for a particular order n could be 89.999 degrees. So we take it as 90 degree. The maximum possible angle of theta is 90 degree, but actually practically 90 degree means going to be like this vertically, so you can't keep a screen there. It's going to be parallel to the screen. But if it is 89.99 degree, yes, somewhere here it will reach the screen, far away from the screen, is it? So theoretically we calculate when theta becomes 90 degree, how many orders will be there? What could be the number of order, right? So theta equal 90. So we take d sine 90 gives the n maximum order. Maximum order occurs when theta equal 90. Okay, we'll calculate now. So we'll know sine 91. D already we calculated 1.667 into 10 to the power minus 6. Sine 91 equal n max into the lambda 450 into 10 to the power minus 9. So the n max, the maximum order that could be created on the screen, n max becomes 3.70. But 3.70 can't be a fraction. It should be the number of orders of fringes must be integers. So the closest integer for this one, 0.7, means there's no possibility, so it should be 3. So the maximum order, we can go up to third order bright band. So on one side third order, so there will be, except the 0th order, there will be 1, 2, 3, 1, 2, 3. So total number of bands or total fringes equal, on one side 3, on the other side 3, the 0th order 1. So it's going to be 7. Okay, so this is the fourth question. So a diffraction grating has 400 lines per millimeter. It is kept at a distance of 1 meter from the screen. Light of wavelength 600 nanometers focus on the grating. Find the total number of bright fringes seen on the screen. So same thing like what I did just now, first part. So the first part, I need to find the maximum order. How many orders will be seen? Then multiply by 2 plus 1, is it? The plus 1 is due to the 0th order. So d sine theta equal in lambda. The maximum number of order occurs when theta becomes 90 degree. Theoretically, we take that way. So before that, I should find the d. So d is equal to 1 into 10 to the power minus 3 meters divided by 400. So it's going to be, I explained this in the theory also, how to find the d. Go through the theory again if you want. So 2.5 10 to the power minus 6. Okay, so d sine theta maximum. So d sine 90 equal to n maximum. So the n becomes maximum, n max lambda. So I need to find the n max. So sine 91, d I know that 2.5 10 to the power minus 6 sine 91 n max into lambda 600 nanometer, 600 into 10 to the power minus 9. Okay, so find the n max, the integer, the close in max comes like 4.17, but we can't take 4.1, so it should be integer. So 4th order, we'll see. So on the screen, maximum fourth order fringe will be produced or created. So total number of fringes on either side of the 0th order, 4th order, 4th order. So 4 plus 4 plus 0th order 1, it will be 9. So 9 fringes will be seen. Okay, so second part, find the distance between the first bright fringe and the second bright fringe on the screen. So this is the grating, I can consider this is the grating. So this is the screen. So laser torch is kept here. So the 0th order will be formed here. This is the 0th order. First order here, n equal 1, n equal 2, second order. So I need to find the distance between first order and second order. So I can't find it directly. I need to find this one, then this one, and subtract it. So we'll see this distance from 0th order to first order, let it be x1, this distance. So I'll say this distance x1, 0th to first order x1, 0th to second order, let it be x2, this distance x2. I'll mark it here. I'll mark it here. This is x2 from here to here, x2. I'll mark it here, x2. So also I need to find theta 1, the angle of diffraction for the first order, that is theta 1. This is theta 2 for the whole angle, theta 2 for the second order fringe. Okay, and also we know the distance of the screen from the grating. This is kept at 1 meter. So this is 1 meter. Okay, so except using those equations d sine theta and lambda and tan theta equal x over d, that's all. So two equations we are going to use. This is theta 1. Okay, theta 1 is the angle of diffraction for the first order. Theta 2 is the angle of diffraction for the second order. Okay, so I'll use the equation first. D sine theta equal n lambda for the first order. So d sine theta equal n lambda. For the first order, if I use, so anyway, I need to find the d first. I already found the d in the previous question, that is 2.5 10 to the power minus 6. I already found it for the first part. So I'll use that same d, 2.5 10 to the power minus 6 sine theta 1 equal n equal 1 first order, lambda equal 600 nanometers, 600 into 10 to the power minus 9. Find the theta 1 here. You know how to solve it. Your calculator must be in degree mode, not radian mode, degree mode. So theta 1 will be 13.9 degree. Okay, so now consider this right angle triangle to find the x1. So tan theta 1 equal x1 over distance d, that is 1 meter. 1. The distance from the screen to the grating, this is 1 meter. The capital D I use in my theory. So that is D. Opposite over adjacent. Opposite is x1 I need to find. Over 1 meter is tan theta 1. So tan theta 1 means tan theta 1 is 13.9 degree equal x1 divided by 1. So find the x1. You'll get it in meters. So x1 will be 0.25 meters. That is the distance of the first order from the 0th order, x1 is 0.25 meters. Same way, find the x2. So again use d sine theta equal n lambda for the second order. So that is 2.5 10 to the power minus 6 sine theta 2 equals second order. So n should be 2 into 600 into 10 to the power minus 9. So find the theta 2 here, the angle of diffraction for the second order. Find it. Theta 2 will be equal to 28.7 degree. So now use tan theta 2 equal tan theta 2, this right angle triangle, tan theta 2 is opposite, that is x2 over 1 meter. So tan theta 2 means tan theta 2 28.7 equal x2 over 1. Find x2. So x2 will be equal to 0.55 meters. So the distance between the first order and the second order, distance between first order and second order, that's the question. So distance between first order and second order, and second order, (0.55) minus 0.25, that is 0.30 meter. Okay, I told that in the theory. The distance between 0th order and first order 0.25, between first order and second order 0.30, increasing. Same way, try find the distance between second order and third order, find it, that will be more than 0.3. So the distance between the adjacent orders will increase. I already explained that in my theory. Okay, so the fifth question, light of wavelength 700 nanometers focused on a diffraction grating. A screen is kept at a distance of 1 meter from the diffraction grating. On the screen, the second order bright fringe is seen at a distance of 46 meters from the 0th order bright fringe. Find the number of lines per millimeter on the diffraction grating. So if I consider this is the diffraction grating and this is the screen, the 0th order is here, second order is here, so the angle theta 2 we need to find it. This distance is given, the distance of the screen from the grating is 1 meter, and the distance of the second bright band from the 0th order, this distance is given as 46 centimeter. This is 1 meter. Right, so I need to find the number of lines per millimeter or number of slits per millimeter on the diffraction gradient. So the only equation we know is d sine theta equal n lambda. We'll use that equation. So d sine theta equal n lambda. So I need to find the d into, okay, I need to find the sine theta first, theta. So we'll find that one first. Then we'll come back to this equation. So tan theta we can use tan theta 2, second order, so I put tan theta 2. So tan theta 2 equal opposite, in I consider this right angle triangle, this is 90 degree, 46 centimeter, this is 1 meter, so 0.46 meter, 0.46 meter divided by 1 meter. So from this find the theta 2, so that will be 24.7 degree. You can put 46 over 100 or 0.46 over 1. Either way, same unit, numerator, denominator. Okay, so that's going to be 24.7 degree. That's a theta 2 angle of diffraction for the second order bright band. Now we'll use the usual equation, d sine theta equal n lambda. D I need to find, sine, this is 24.7 equal second order, so n equal 2. Lambda is given 700 nanometer 10 to the power minus 9. Find the d. So you will get d is equal to 3.35 10 to the power minus 6 meter. The question is find the number of lines per millimeter. So this is, I got it in meters. So d equal, d has 3.35 10 to the power minus 6 meter. That's the distance between the adjacent or next to next slits is this much of meter. If I convert to millimeter, multiply by 1000, so that's going to be 3.35 10 to the power minus 3 millimeter. Okay, I told that in the theory when I start, the relationship between the distance between the adjacent slits and the number of slits per millimeter, d is equal to 1 over n. I use n, not a usual notation, but I am using it. N stands for number of lines per millimeter. So if I keep this in millimeter, this will be number of lines per millimeter. If I keep this in meter, this will be number of lines per meter. Carefully choose the unit. Here they ask per millimeter, so d must be in millimeter. So n is going to be 1 over d. d is 3.35 10 to the power minus 3 per millimeter. So it's going to be 299 per millimeter, approximately 300 lines per millimeter. so similar type of question appeared in the past paper. That is, January 2021. So the same type of question, exactly the same, only the numbers are different. January 2021. Okay, so that's the question. Sixth question I'm discussing, that one. The same as what I did as a fifth question. It's appeared in the Edexcel IAL Unit 2 paper WPH 1201, question number 18, January 2021. The A part is describe how a teacher can demonstrate that the light from a laser pointer is a plane polarized. So we haven't done polarized, I'll discuss it later. So B part, first part, the equation is given. N lambda equal d sine theta, state the quantity represented by d. You know the distance between the adjacent slits or adjacent lines on the diffraction grating. Okay, second part is the question. So in the second part, question number 18 this year, the teacher made the following measurements. Distance from the central maximum to first order maximum given. So central maximum to first order maximum 1.61. So I will put it on diagram rather than writing the whole question. So this is the diffraction grating. So this is the screen. So this is the zeroth order. This is the first order. So the distance between the central maximum, normally we all central maximum of zeroth order, to the first order is 1.61. So this distance is 1.61 meters. Distance from the diffraction grating to the screen 2.74. The wavelength of the light from the laser pointer also given. Lambda is given as 532. Lambda is 532 nanometer. This is question number 18. Part B on that year, part B, second part. Okay, you can try later. I'm not doing the full. Calculate the number of lines per millimeter on the diffraction. It's same, exactly the same. You need to find the theta. This is first order. Theta, find it. Tan theta equal 1.61 over 2.74. Find the theta. You will get theta will be equal to 30.4. Then use the equation d sine theta equal n lambda. Here it's first order, so d sine 30.4 equal 1 into lambda is given, wavelength 532, 10 to the power minus 9. Find the d. You will get d is equal to 1.051 into 10 to the power minus 6 meter. If you write it in millimeter, 1.051 into 10 to the power minus 3 millimeter. So number of lines per millimeter, equal 1 over d. So you will get 951 per millimeter, number of lines per millimeter, 951 per millimeter. That's the B part, second part, question number 18, January 2021. Okay, so the third part of the question, using this diffraction grating and laser pointer, only the first order maxima and the central maximum are produced. Explain how the teacher using the same laser pointer could improve his value for the number of lines per millimeter. Okay, so they are calculating, this is the experiment they are doing it. How can we improve the value? So only thing you need to reduce the percentage uncertainty. So here they told the distance from the zeroth order to first order. They are saying on the screen you are able to see only up to first order, means there will be first order on the other side also. So rather than measuring the distance of first order from zeroth order, you know that unit 3 you would have learned in unit 3. When you increase the measurement, percentage uncertainty will be reduced. Percentage uncertainty means uncertainty over measurement into 100. Uncertainty divided by measurement into 100. That is the percentage uncertainty, unit 3. So when you increase the measurement, the value of the measurement, percentage uncertainty could be reduced. So here, anyway, you need to find this value 1.61, but instead of measuring this length, you can measure the distance from n equal 1 to n equal 1. So when you measure this distance and divide by 2, measure this distance and divide by 2. But you are increasing the measurement. So when you are increasing the measurement, percentage uncertainty will be reduced. One advantage, the first thing you should know to increase the accuracy of this answer. First answer you should say, measure the distance from first order to first order, then divide by 2 to find the distance of the first order from the zeroth order. But measurement must be taken from first order to first order. Hence, the percentage uncertainty will be reduced. One answer. The second answer, increase the distance of the screen from the grating. By increasing the distance of the screen from the grating, there also you can reduce the percentage uncertainty in the measurement. So second answer you should say, increase the distance of the screen from the grating. There also percentage uncertainty of the measurement could be reduced. So those are the two answers for that question. Again, the same type of question appeared in October 2022. October 2022, question 18. I'll just briefly discuss it now. Okay, question number 7, October 2022, question number 18, WPH 120201. So this diagram is given. A student directed light from a laser so that the light was incident on a diffraction grating at 90 degree. The student placed a screen a distance x from the grating, so x from the grating, and observed a series of bright maxima of order n on the screen. The student determined the value of theta 1 shown on the diagram. Okay, so the angle theta 1 is 14 degrees. So that's given in the question. The angle theta 1 is 14 degrees. The first part, calculate theta 2. That's the first part of this question. Okay, so how to calculate the theta 2? We know that sine theta equal n lambda. So theta 1 14 means that's for the first order. So sine 14 equal n equal 1 into lambda. Sorry, d sine theta, d is missing. So sine 14 equal lambda over d. Okay. Now the question is, bring the d down. So lambda over d is sine 14. The question is find the theta 2. So when sine theta 2 n equal 2. So d sine theta 2 equal n equal 2 into lambda. So sine theta 2 equal 2 into lambda over d. So we know that lambda over d is sine 14. Find the value of sine 14. Or you can directly use that value here. So sine 14. So you can find the value of sine 14 and substitute it here, or it's mathematics now, or you can divide it, these two equations, anything you can do, but it's simple. You can find the sine 14 lambda over d. So instead of lambda over d you put sine 14. So anyway, anything you can do, that is sine theta 2 equal 2 times sine 14. Solve it right side. Sine 14 is a number, 2 is a number, find the value of it, then take inverse of sine, you will get the theta 2. Okay, so find the sine 14 into 2, that is 0.484. Take inverse of it, you will get the theta 2. That's the first part, A part. That's the answer question for the A part, this paper. That's the A part, not first part, A part. B part, the same paper, same exam paper. The student measured theta for values of n from 1 to 4. Describe how graphical method can be used to determine the value of the light from the laser. Assume that the value of the grating spacing d is known. D we know, we assume it. Okay, so we'll say d sine theta equal n lambda. So he's measuring the values. The student measured theta for the values of n. So for different n up to 4, he's measuring the theta. I need to find the lambda by using a graph. So we'll say sine theta equal n is a variable, theta is a variable, lambda and d are constant. So lambda over d times n. So plot a graph of sine theta against n. So sine theta equal lambda over d into n. This is in the form of y. This is in the form of gradient m. This is the x-axis. You will get a straight line through the origin. This is n. You will get a straight line through the origin. Find the gradient from the graph. So gradient is going to be lambda over d. We know the d they are saying. So lambda equal d times gradient. Hence we can find the lambda. That's the aim of the practical. Question number 18, October 2022. This all. Okay, the same paper, Edexcel IAL Unit 2, October 2022, question number 18. Part C, it says, in a separate experiment, the student uses a different diffraction grating, different one, not the same one, different diffraction grating that has been labeled 300 lines per millimeter by another student. The distance measured on the screen between n equals 0 maximum and n equal 2 maximum 0.397. Exactly the question what I did start of this question number 5. So the student is measured. So I can say that this is the grating, this is the screen. So this is the 0th order. The line goes. This is 0th order, and between the n equal 2. So the order between these two, student measures the distance 0.397. Distance, deduce whether the labeling of the diffraction grating is correct. So someone labeled the diffraction grating 300 lines per millimeter. Whether is it right? That's a question, right? So the distance between the screen and the grating, that is x, they marked it here. The x is given, the value of x is given 2.000 meters, 2.000 meters. And wavelength of the laser they used, that also given, lambda is given 650 nanometer. Okay, so it's labeled 300 300 lines per millimeter. Is it correct? Same thing what I did earlier. I'm not going to do that. I'll give you the idea. Same thing, you are going to find the theta here. Use tan theta equal for the second order 0.397 over 2.00. Find the theta. So you will get theta is equal to 11.2 degree. Then d sine theta equal n lambda, d sine 11.2 equal n2, because second order, the distance of the second order they said this much, 2 into lambda from 650 10 to the power minus 9. Find the d. So you will get d in meters because lambda is given in meters. So 6.693 10 to the power minus 6 meters. In millimeter, multiply by 1000, 6.693 10 to the power minus 3 millimeter. So number of lines per millimeter, I use n, which is not a standard notation, I am using just for quickly finishing. N equal 1 over d, so 1 over 6.693 10 to the power minus 3 per millimeter. So when you solve, you will get 149 per millimeter, but they are saying 300 per millimeter, so it's a wrong labeling. The labeling is incorrect. It's not correct. 300 lines per millimeter is not a correct labeling that you should tell here. You should write that. It's not a correct labeling. Okay, so this question, eighth question, blue light of wavelength 400 nanometer and orange light of wavelength 600 nanometer, both are coherent sources, right? Coherent, otherwise the fringe pattern will scroll. Are projected on a diffraction grating at the same time. A screen is kept behind the grating. Grating has 300 lines per millimeter. Okay, the question is find the maximum order of blue and orange bright fringes seen on the screen. Order, they are not asking how many fringes, order. So earlier also we found the order, then we multiply by 2 and add plus 1 because the zeroth order. Here just it's a number of orders. So the first part for blue, d sine theta equal n lambda, n blue maximum equal to d sine 90 over lambda. Is it d sine 90 over lambda? So we need to find the d, that is 300 lines per millimeter. So we need to find d first. Actually I would have done that one first. So d will be equal to d is equal to 1 into 10 to the power minus 3 meter divided by 300. So that will be equal to 3.33 10 to the power minus 6 meter. Then for blue color, d sine theta equal n lambda. So we know d, that is 3.33 10 to the power minus 6 times sine 90 equal to n maximum blue, n blue maximum into wavelength of blue 400 nanometer 10 to the power minus 9. So we'll get NB maximum, the maximum number of orders of blue, that will be equal to 8. You'll get decimal values, but we need to approximate to the whole number. So maximum blue will be 8. Then for orange, if I do same way, same equation, d sine theta equal n lambda for orange. So d is 3.33 10 to the power minus 6 sine 90 equal n orange maximum into 600 10 to the power minus 9. Say n orange maximum, that will be equal to 5. You will get decimal, but the whole number is the order. So 5. So there will be 8 order of blue fringes and 5 order of orange fringes will be same. Second part, which orders of blue and orange fringes will overlap on the screen? Okay, so they will have different angle of diffraction. Say for example, if you consider first order of blue and first order of orange, it will be different because we know for first order n equal 1, d is the same for both, n equal 1, but lambda blue is smaller, so the angle of diffraction of blue will be smaller first order. Same way for angle of diffraction of orange first order will be more than the angle of diffraction of first order of the blue. So like that, they are not going to overlap. First order won't overlap. But sometimes it could be something like blue color, for example, I am saying, for example, blue color second order third order and orange color second order. Like that, different orders might overlap. We are going to see which orders are going to overlap. Order of bright bands are going to overlap. If they want to overlap, the angle of diffraction should be the same for both bands. Those are overlapping. they should have the same theta. The theta same, that means x will be the same because tan theta equal x over d. See the theory what I did today. Tan theta equal x over d. X is the distance from the zeroth order. So theta same for both mean x will be same for both, but x could be different orders of blue and orange. Okay, so that's idea. Theta should be the same. So if I think that way, if I take that idea, second part, d sine theta equal n lambda, sine theta equal n lambda over d. We don't know which orders are overlapping, but they should have, if they overlap, different orders of blue and orange will overlap, but they should have the same angle theta. Okay, so in that case, when they overlap, blue and red, so when they overlap, on the screen, theta should be same for both orders. Right, so n blue, lambda blue, d, this is sine theta, equal n orange, lambda orange over d. D and d will get cancelled. NB, lambda blue is 400 nanometer. Nano I can give because this is also going to be the same unit nano. N orange into 600 nano, 10 to the power minus 9, 10 to the power minus 9 will get cancelled. So N blue over N orange, if I consider, NB over NO is going to be 600 over 400. That's going to be 3 over 2. That means third order of blue and second order of orange will overlap. Also, sixth order of blue and fourth order of orange will overlap. We found it in the first part. There will be 8 orders of blue. So, up to 6th order, they can overlap. So, third order of blue and second order of orange will overlap. Okay, the second part, which order of blue and orange fringes will overlap is the question. So, if they want to overlap, the condition, they should have the same angle theta. So, they can have different orders of blue and red could overlap, but they should have the same angle of theta. If they have same angle of theta, then the x will be the same because tan theta equal x over d. So x is the position from 0th order, the distance from the 0th order. So they should have the same theta. I wrote the answer already. So d sine theta equal n lambda. So we first part we found the already we found the maximum number of blue and orange that could be created. So here we'll use d sine theta equal n lambda, sine theta equal n lambda over d. When they overlap on the screen, they should have the same theta. So when I consider same theta means when I make the sine theta, nb lambda dd, that is for the blue color, the theta should be equal to same for the orange color, but they can have different orders. Blue and orange could be different orders of bright bands, but they should have the same theta because they should be physically on the same position on the screen means tan theta equal x over d. So theta should be the same, then x will be the same, right? So that idea. So d and d will get cancelled. NB into 400, NB into lambda b is 400 equal NO into 600. D and D get cancelled. So NB over NO will be 600 over 400, 3 over 2. So the ratio of the blue order to the orange order when they overlap should be 3:2. So they can overlap like this. Third order of blue and second order of orange can overlap. The next thing, sixth order of blue and fourth order of orange can overlap. But ninth order of blue and sixth order of orange won't overlap because we already found in the first part the maximum number of orders for the blue is 8 and orange 5. So the maximum number of orders are limited. So the possibility of overlapping third order of blue and second order of orange or sixth order of blue and fourth order of orange. Okay, so that's the end of this sixth lesson related to diffraction grating. I hope you understood. If you subscribe my channel, you'll get notification when I upload the next video. Also, you can navigate to any video that you want to watch by using the playlist. There I have categorized or grouped all my videos into different groups at different titles, so you can follow the playlist to navigate to the required video. Okay then, bye.